In this video, we're going to focus on the Otto cycle of an internal combustion engine. First, we're going to work on solving some basic problems, and then we're going to discuss the PV diagram of an Otto cycle. So in this example, we have an Otto cycle of an internal combustion engine, and it has a compression ratio of 8, represented by the symbol R, and a gamma ratio of 1.4. Calculate the efficiency of this engine. The gamma ratio is the ratio between the molar heat capacity at constant pressure and the molar heat capacity at constant volume. Now for the compression ratio, in the first step of an Otto cycle, you have an adiabatic compression or compression stroke. And so initially, the volume is going to be relatively high. So let's say VL for a large volume. And during compression, the volume will decrease as the piston moves up. And so the volume is smaller. The compression ratio is the ratio between the large volume and the small volume. So it's a value that's typically greater than 1. Now let's focus on finishing this problem. So the efficiency is equal to 1 minus 1 divided by R raised to the gamma minus 1. So in this example, the compression ratio is 8, and gamma is 1.4. And 1.4 minus 1 is 0.4. Now 8 raised to the 0.4, that's equal to 2.2974. And 1 over 2.2974, that's 0.4353. And that shouldn't be in a fraction anymore. So 1 minus that number, that's equal to 0.56. So that's the efficiency. And if we multiply it by 100, we could say that it's 56% efficient. So this is the answer. Now let's focus on number 2. The efficiency of a combustion engine is 45%. Using a gamma ratio of 1.4, calculate the compression ratio of the engine. So this time we need to solve for R. So let's start with this formula. Efficiency is 1 minus 1 over R raised to the gamma minus 1. So how can we get R by itself? So I'm going to take this fraction, move it to this side. So the sign is going to change from negative to positive. Then I'm going to take the efficiency, move it to that side. So it's going to be negative on the right side. Now what I'm going to do is raise both sides to the negative 1. So this is going to flip to the top. So on the left, this is going to be R raised to the gamma minus 1. And on the right, it's going to be 1 over 1 minus E. So for example, x raised to the negative 1 is the same as 1 over x. It simply flips to the other side of the fraction. So now to get R by itself, I need to raise both sides to the reciprocal of that exponent. So that's 1 over gamma minus 1. So here's the formula. The compression ratio is 1 over 1 minus the efficiency raised to the 1 over gamma minus 1. So the efficiency is 45%, which is the same as 0.45. And then we're going to raise it to 1 over 1.4 minus 1. So 1 minus 0.45 is 0.55. And 1.4 minus 1 is 0.4. 1 divided by 0.55, that's 1.81 repeating. And 1 divided by 0.4 is 2.5. So the compression ratio is about 4.5 in this example. Number 3. The efficiency of an internal combustion engine is 52%. So that means it's 0.52. and the compression ratio is 9.2. What is the gamma ratio of the working substance? So let's rearrange the equation, starting with this one. So we need to isolate gamma. So first, I'm going to take this term, move it to that side. So it's going to be 1 over r raised to the gamma minus 1. Then I'm going to move e to that side. So it's going to be 1 minus e. And then just as before, I'm going to raise both sides to the negative 1 power. So r raised to the gamma minus 1 is going to be 1 over 1 minus e. Now here's where it's going to be different. So at this point, I need to take the natural log of both sides. A property of natural logs allows me to take the exponent and move it to the front. So the exponent gamma minus 1 would move towards the left side. So it's going to be gamma minus 1 times the natural log of the compression ratio, and that's going to equal ln 1 over 1 minus e, which is the same as ln 1 minus e raised to the negative 1, which means I can take this and move it over here. So I'm going to divide both sides at this point by ln r. So gamma minus 1 is going to equal negative natural log 1 minus the efficiency divided by ln r. Now I'm going to add 1 to both sides. I'm going to move this to that side. And so therefore, the gamma ratio is going to be 1 minus the natural log of 1 minus e divided by the natural log of the compression ratio. So this is the formula that you want to use to calculate the gamma ratio. So it's going to be 1 minus the natural log of 1 minus 0.52 divided by the natural log of the compression ratio, which is 9.2. So if you type that in the way you see it, this will give you 1.33 for the gamma ratio, which sounds like a reasonable answer. So that's it for this problem. Now let's focus on part B. So given a gamma ratio of 1.33 and the fact that the substance has a molar heat capacity at constant volume, which is 21.47, what is the molar heat capacity of the substance at constant pressure? The gamma ratio is Cp over Cv. So if we multiply both sides by Cv, Cp is going to be equal to the gamma ratio times Cv. So the gamma ratio is, in this example, 1.33, and Cv is 21.47. So Cp should be approximately 28.6 in this example. Now granted, there are some deviations with this formula, so this is just going to give you an estimation. So keep that in mind. Now let's talk about the PV diagram for the Otto cycle. So the first step is an adiabatic compression step. The second step is an isochoric process. The third step is an adiabatic expansion. And the last step is an isochoric process as well. So let's call this A, B, C, D. So we have pressure on the y-axis and volume on the x-axis. So the first step is going from A to B. So as we go from A to B, this is the compression stroke. It's an adiabatic compression. Now, anytime a gas is compressed, the work performed by that gas is going to be negative. So the work is really done on the gas. It's not really done by the gas. If the work is done by the gas, work is positive. If it's on the gas, work is negative. So W is negative for this example. And for any adiabatic process, Q is 0. No heat goes into the system or out of the system. Now the change in the internal energy of the system is Q minus W. And since Q is 0, delta U is equal to negative W. And delta U is always equal to NCV delta T. So W in this example is NCV delta T. Now, since we're going from A to B, the change in temperature is going to be the temperature at B minus the initial temperature at A. And let's not forget the negative sign. Now, for an adiabatic process, we have this formula. T1V1 raised to the gamma ratio minus 1 is equal to T2V2 raised to the gamma ratio minus 1. Now, we're going from A to B, so T1 could be called TA, V1 is VA. And that's a terrible gamma symbol. So T2 is going to be the temperature at B, V2 is the volume at B. Now the volume here, let's call it V. So if the volume at B is V, the volume at A is RV. So the compression ratio is the ratio between the large volume, which is the volume at A, divided by the small volume, which is the volume at B. So now you can see how the compression ratio is related to the Otto cycle in this PV diagram. Now there are some other things that you need to know before we move on to the next step. And that is the gamma ratio is Cp over Cv. It's the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. And Cv is 3 over 2 times R for a monatomic gas like helium, neon, and so forth. Cv is 5 over 2 R for diatomic gases like O2, N2, and so forth. Now sometimes you may have a mixture of gases, so keep that in mind. Cv can also be calculated by using this formula. It's R over the gamma ratio minus 1. And R is this constant, 8.3145 joules per mole per Kelvin. So those are some things that you want to keep in mind. Now let's go over the second step. So that is from B to C. So as we go from B to C, this is an isochoric process. And for an isochoric process, the volume is constant. So the change in volume is 0. And therefore the work done is 0. So let's put W equals 0 for that part. Now notice that the pressure is increasing as we go from B to C. And the only way for that to happen is if the temperature goes up, and the pressure will go up at constant volume. So therefore we have this relation. P1 over T1 is equal to P2 over T2 at constant volume. In order to increase the temperature at constant volume and to increase the pressure, heat has to be added at this point. So therefore this is going to be QH. So that's where heat is added to the system, going from B to C. And no heat is added from A to B. So for this part, Q is 0 for the adiabatic compression. Now we know that delta U is Q minus W. And since W is 0, delta U equals Q for an isochoric process. And delta U is always equal to NCV delta T. So Q, which equals delta U, so we'll call it QH because it's going into the system at this point, it's going to equal N times CV times the change in temperature. So the final temperature is the temperature at point C, the initial temperature is the temperature at point B. And so that's how we can calculate QH if we know the two temperatures. Now let's move on to the next part. So this time we're going from C to D. So the gas is expanded. So the work done is going to be positive for any type of gas expansion. So as we go from C to D, this is an adiabatic process. Specifically, an adiabatic expansion. And so once again, Q is 0 and delta U, which is Q minus W, is going to be negative W. So W, which is negative delta U, that's going to be negative NCV delta T. And so we're going from C to D. So that's going to be the temperature at D minus the temperature at point C. So that's how we can calculate the work for this step. Now we also have another expression. TCVC raised to the gamma minus 1 is equal to TD VD raised to the gamma minus 1 as we go from point C to point D. Now for the last step, going from D to A, so that's an isochoric process. The change in volume is 0 and the work is 0. So this time, the temperature is decreasing as we go from point D to point A, which means the pressure is decreasing. So at this point, heat energy flows out of the system into the cold reservoir. And so that's going to be QC. Now we know that delta U is Q minus W, and because W is 0, delta U is equal to Q. So QC is going to be NCV delta T, but we're going from D to A, so that's going to be the temperature at A minus the temperature at D. Now, because the temperature at A is lower than the temperature at D, QC is going to be negative, which means that heat energy leaves the system. So make sure you understand that QC is negative, QH is positive. Whenever energy enters the system, it's an endothermic process. When it leaves the system, it's exothermic, so Q is negative. Now to calculate the work, it's equal to the area enclosed by this cyclic process. You could also calculate the work using this formula. It's QH plus QC, where QC is a negative value. Now if you want to use positive values, then it's the absolute value of QH minus the absolute value of QC. So that's how you can calculate the work performed in one cycle of this internal combustion engine. Number 4. The temperature of a gasoline air mixture is 300 Kelvin when it enters the cylinder at point A. So the temperature at point A is 300 Kelvin. The gamma ratio is 1.4 and the compression ratio is 8.7. Calculate the temperature at the end of the adiabatic compression at point B. So what formula should we use to calculate this? Well, we can use this equation. TAVA raised to the gamma minus 1 is equal to TBVB raised to the gamma minus 1. Now what I'm going to do is I'm going to divide both sides by TA and by VB. So on the left, these will cancel. On the right, these will cancel. And so what I have is VA raised to the gamma minus 1 over VB. I can distribute the exponents of both of those terms. That's equal to TB over TA. Now, it's important to understand that this is V and this is RV. So VA is the compression ratio times V, and VB is simply V. So I'm going to replace VA with RV and VB with V. So I can cancel V. And then I'm going to multiply both sides by TA. So TB is TA times the compression ratio raised to the gamma minus 1. So now let's calculate TB. So TA is 300 Kelvin. If it's in Celsius, you need to add 273 to convert it to Kelvin. And the compression ratio in this example is 8.7 raised to the 1.4 minus 1. So TB in this example is 712.7 Kelvin. And so that's the answer for part A. Now let's move on to part B. If the pressure of the gasoline air mixture is 0.92 atm at point A, what is the pressure at point B? So during an adiabatic compression, we know that the volume decreases and the temperature goes up and the pressure goes up. We can see that the temperature changed from 300 to 712.7 Kelvin. And as you go from A to B, it's going up in the y-axis. So whenever the volume, temperature, and pressure changes, we need to deal with the combined gas law. P1V1 over T1 is equal to P2V2 over T2. So in this case, we can replace 1 with A, 2 with B. So we can say it's PA VA over TA is equal to PB VB over TB. Now let's make some space. So now let's cross multiply. So on the left it's going to be TA PB VB, and that's going to equal PA VA TB. So I'm going to solve for PB. So I'm going to divide both sides by TA and VB. So the pressure at point B is going to be PA times VA over VB times TB over TA. And if you recall, we said that VA is equal to RV and VB is equal to V. So VA over VB is equal to the compression ratio R. So the pressure at point B is equal to the pressure at point A times the ratio of the temperature at B to the temperature at A times this, which is the compression ratio R. So at point A, the pressure is given to us as 0.92 atm. The temperature at point B is 712.7 Kelvin, and the temperature at A is this value, 300 Kelvin. And the compression ratio in this problem is 8.7. So the pressure increases greatly during a compression stroke. It's 19.01 atm. As you can see, it's a lot higher than what it was before. So if we take 19.01 and divide it by 0.92, the pressure increases by a factor of 20.7. So during a compression stroke, the pressure greatly increases. The temperature increases slightly. It did a little bit more than doubled, but the pressure greatly increased during this compression stroke.